Hey there, awesome physics students. Today we want to talk about torque and forces, and in particular static equilibrium, in which the sum of the forces is zero and the sum of the torques is zero too. So it's pretty simple in terms of physics ideas. It's mostly about problem solving. So let's go ahead and work on an example to start with. So the essential idea with statics is that the sum of the forces is zero and the sum of the torques is zero. And notice I was vague here when I said the sum of the torques is zero. This is the torque about any axis, okay? And we're going to use this idea in the future, so you want to remember this. Now, this fact that the sum of the forces is zero is actually three equations, because forces is a three-dimensional vector. And so this tells you that the sum of the forces in the x direction is zero, the sum of the forces in the y direction is zero, and the sum of the forces in the z direction is also zero. Now, usually we're going to do problems that are two-dimensional. So we mostly just need these two, and then we need this. Okay. The why are all these zero? The reason that there is zero is because the acceleration is equal to zero and the angular acceleration is equal to zero. So there's no angular acceleration either. And the basic idea is that nothing is moving and it's not accelerating either. Okay, so let's look at a problem. I think you really see what this is about when you actually look at a problem. So let's look at a problem here. We have a 5-meter long ladder. So let me just be clear about this. This ladder is 5 meters long. So this is the ladder here. That length is 5 meters long. It touches a wall 4 meters above a cement floor. The ladder is uniform, so that means that there's a center of mass is in the middle of it, and it has a mass of 12 kilograms. Assuming the wall is frictionless, so we're going to assume really not any significant friction on the wall, but there must be significant friction on the floor. And I think you can see that, because if there were not significant friction on the floor, it would just slide down. So we are asked to determine the forces exerted by the floor and the wall on the ladder. So with these things, we're going to follow a process for problem solving. It's going to be very similar to the one we used before. Okay, remember that we always draw a picture of our situation here. So this is 5 meters. This is 4 meters. And I don't know if you recall, but there's a very common right triangle. This is a right triangle. The hypotenuse is the 5 meters. Very common right triangle is the 3, 4, 5 right triangle. So this is actually going to be 3 meters on the side here. Okay, so it's important to note that dimension. The other thing we notice is that because the ladder is uniform, this means that the force of gravity acts in the center of mass of the ladder. So that's going to be the weight of the ladder pulling down. And they say that assuming the wall is frictionless, so the wall being frictionless, recall that there's two kinds of contact forces. There's friction, which is parallel to the surface, and then there's the normal force, and normal means perpendicular. So that one is perpendicular to the surface. Saying it's frictionless, so there's no force on the ladder parallel to the surface, but the only force on the ladder then is going to be perpendicular to the surface, so it's going to point like that. So that is the force from the wall on the ladder. So they use FW here. The floor is not frictionless. So the floor is both going to have a friction force that keeps the ladder from sliding down, right? Because this thing would want to slide, it would naturally want to slide that way, and friction opposes the motion. And there's also, of course, going to be a normal force from the ladder, from the floor on the ladder, okay? Now they have drawn this as just a force at point C, and they've just decomposed it into X and Y components. But I'm going to just call them normal and friction, just because I think that that connects better with what we learned before. Okay, so we want to find the, we need to find the forces exerted by the floor and the wall on the ladder. So we need to find FW, we need to find the frictional force, and we need to find the normal force. Okay, so how do we do this? We've kind of basically just drawn the free body diagram with the forces where they act and maybe some dimensions here like the 4 meters and the 3 meters. So one thing that we're going to want to do is we are going to want to solve the sum of the forces equation. So we're going to add up the forces in the x direction, add up the forces in the y direction, and set those equal to 0, right? Because we want the acceleration of this is going to be 0. So let's go ahead and sum the forces in the x direction. We'll use a standard XY coordinate system. This is what they use here. So in the x direction, we have the force of friction, that's positive, and we have the force of from the wall, that's in the negative x direction. And that's the only, those are the only two forces in the x direction. So that I'm going to set that equal to ma in the x direction, but a in the x direction is 0, so these are 0. So this tells you that the force of friction has to be equal to the force from the wall. Okay. Now let's do the y equation. The y equation says that, well, I have the normal force up, and that's a positive force, and then I have gravity down, that's a negative force. And I set that equal to ma in the y direction, and of course a in the y direction is 0 because it's statics. And in statics, the accelerations are always 0. It's beautiful. And again, I can solve for the normal force here with this equation, and that tells me that the normal force is equal to the weight of the ladder. Okay, so that's great, but I still don't know what these are. I guess I know what the normal force is. The normal force is equal to mg, but mg is equal to 12 kilograms times 9.8 newtons per kilogram. And that gives me, let me just compute that real quick here. That's going to be 108, I'm going to round this off, 118 newtons. Okay, so this one, we've got this one, the normal force, that's 118 newtons. But we still need to know about the friction and the wall force. We don't know either of these. We know they're equal to each other. So once we find one, we have the other. The problem is that we had 3 unknowns here, but only 2 equations, right? We just use this two dimensions, x and y. We need another equation. So to do that, we're going to use our torque equation. We know that the sum of the torques must be equal to 0, and we can use any axis for this. Okay, so we can put the axis anywhere, and this is going to be true. Now, in these problems, it's a very useful problem-solving tactic to choose your axis where there's an unknown force. Choose your axis where there's a force that you don't know about and don't care about. So let's decide, let's find the force from the wall first. So that means that we don't know the force of friction, and right now we don't care. So if that's what our goal is going to be, to find the wall force, and we don't care about the force of friction, we should put our axis here. So let's place our axis here. Let's call this point A. And so we'll sum the torques about the point A. And the reason A is a good choice in general, actually, is just because, look, there's 2 forces down there, the normal force and friction. And, you know, if I put my axis there, the distance from the axis to where the forces act for those 2 forces is 0. So I don't have torques from those 2 forces. So if I put my axis here, I only have a torque from gravity and a torque from the wall force. If I put my axis somewhere else, I'll have more torques. So if I choose the axis to be down here, it just makes it easier. There's fewer torques. Okay, so let's go ahead and start. The center of mass of the ladder is well, let's take them force by force. So there's a torque from gravity, and so remember our R vector points from the axis to the place where the force acts. So that is going to be 2.5 meters because the ladder is 5 meters long, and then I need to multiply that by the weight of the ladder. So that's mg, that's the force, right? So I'm following this paradigm, R times F times the sine of the angle between these. So this is the angle. I'm going to call this the angle between them, and I'll find that angle in just a minute here. Okay, so I just take RF sine theta, and then I also need to know, okay, I'm going to use the standard counterclockwise is positive. Is this going to cause, is this force mg going to cause clockwise or counterclockwise rotation around the axis point? Well, I think it's, you can see it's going to cause clockwise rotation. And so that means it's going to be a negative torque. So I need to put a negative in by hand. Okay. Then I look at the next torque. That's going to be from the force from the wall up here. My R vector in that case is all the way up there. That's the full 5 meters. So let me just do 5 meters. And then that force is FW, which I don't know. And then the angle between that force and the R vector, I'm going to call this, I would call it theta, but I already used, this is theta, right? Which is theta here. So this is actually 90 minus theta. Okay, so I'm going to multiply this by sine of 90 minus theta. Okay. And that is going to cause a counterclockwise torque about this axis point down here based on the direction of that force. And so this is going to be a positive torque. Okay, so I have only 2 torques and there's no angular acceleration. So I set this equal to 0. Okay, so let me go ahead and find the angle theta. So if I look at the angle theta here, I call this theta. This is 5 and this is 4. So I know the adjacent side and the opposite side. So that suggests that if I use sine of theta, then that is going to be, oops, not sine of theta, cosine of theta. Oh, sorry, this is 3. So sine of theta is actually going to be the opposite side. That's 3 over the hypotenuse, which is 5. So actually, I don't even need to find the angle per se. I can just use the fact that sine here is 3 over 5. And similarly here, sine of 90 degrees, sine of 90 minus theta is just going to be equal to cosine of theta. And that's just a complementary law that arises from the basic definitions of sine and cosine. Cosine is adjacent over hypotenuse, so that's going to be 4, which is adjacent over hypotenuse, which is 5, so 4 over 5. So this is 4 over 5 right there. And this is 3 over 5. Okay, so I don't even need to find the angles. Okay, so let me take a second to rewrite this down here and do a little algebra on this. Okay, so I rewrote this equation here, down here with all of the numbers in, and you can see I have everything is numbers except right there. That's our variable. That's what we're trying to find, the force from the wall. So I just need to do a little more algebra. I'll move this to the other side, and then I'll divide by these 2 and solve for the force from the wall. So let me just do that real quick here. Okay, so I've solved for this, and I've just put all the numbers in. I took all the units out just to make it a little more clear. And so I can just plug this into my calculator. And when I do, I type this into my calculator, I get 44 newtons. So the wall force is 44 newtons. Okay, so that one, so now let me just come back up here. I know what that one is. Now, the last thing for me to do is to find this frictional force here. But if you recall, this equation here from my sum of the forces told me that the friction force and the wall force had to be equal and opposite. Okay, those are the only two horizontal forces on this free body diagram. So that also tells me that the frictional force must also be 44 newtons. Okay, so now I know all of these. I know the normal force is 118. I know the wall force is 44 and the frictional force is 44. Okay, so I'll do another example. I think examples are really the best thing to see here. Do another example in a different video, but hopefully this is clear and you get the idea. One of the main ideas here is that you can sum the torques about any axis, and actually you get a lot of work from this equation. Many students I see are very hesitant to start by summing the torques. And it actually goes faster if you begin the problem by summing the torques and then sum the forces. So don't be shy with this, summing the torques. Do it right away. Pick it at an axis. Use an axis where there's a force that you don't know about and that you don't care about. And that will help you a lot in your problem solving. All right, I'll see you guys in another video. Bye.